I want you to imagine a scenario for a second. It's a crisp, beautiful autumn day, right? You're out for a hike in this stunning high-latitude pine forest,
Sounds pretty ideal, honestly.
right? The air is fresh, the leaves are turning that perfect burnt orange color, and as you're, walking off the beaten path, you spot a cluster of wild mushrooms.
Oh, nice.
Yeah, and let's say you're a bit of a foraging enthusiast. So you gather them up, you brush off the damp soil, and you toss them in your basket.
Standard foraging trip.
Exactly. You take them home, fire up the stove, and make this incredibly delicious, rich, buttery mushroom stew for dinner. You eat it, you go to bed, and you wake up the next morning feeling perfectly fine.
Completely normal.
Totally normal. You go to work, you live your life, a whole week goes by, maybe even 2 full weeks go by, and you have completely, entirely forgotten about the stew at this point.
Which you would, yeah.
But then suddenly, literally out of nowhere, your kidneys they just stop working.
It is a genuinely terrifying timeline. You have this totally innocuous meal, followed by weeks of absolute silence, and then it just culminates in total organ failure.
It's wild.
It really is. And that delayed silent fuse is, well, it's what makes the subject of our deep dive today so biologically unique and, historically speaking, so incredibly dangerous to humans.
So today we are diving into a stack of really fascinating sources. We've got mycological taxonomy papers, toxicology reports, and even some cutting-edge oncological clinical trials. And the mission for this deep dive is to unpack one of nature's most paradoxical creations.
The Deadly Webcap.
Yes, the Deadly Webcap, or Cortinarius rubellus. We are going to trace how this highly deceptive, lethal fungus operates in the wild. We'll look at the specific chemical mechanics of how it kills.
And this is the part that is just mind-blowing, we'll look at how researchers are currently attempting to harness its deadly precision to actually cure metastatic kidney cancer.
Which is such a wild turn of events.
It's a beautiful, almost poetic irony in the field of medicine, really. I mean, we are looking at a natural toxin that is so ruthlessly effective at destroying one specific human organ, the kidney.
Right.
And it might actually be the only weapon we possess capable of hunting down cancer cells that originate from that very same organ.
It's like the perfect biological paradox.
Yeah.
The ultimate poison becomes the ultimate targeted cure.
Exactly.
So for you listening, whether you're a foraging enthusiast or a medical science nerd, or just wildly curious about nature's hidden assassins, this deep dive is going to completely change how you view the fungal kingdom.
Without a doubt.
But before we can get to the cutting-edge cancer trials, we really have to understand how this mushroom hides in plain sight. Because if you're out foraging, relying on dim forest lighting to tell the difference between what's going in your frying pan and what's going to put you on a dialysis machine, you really need to know what you're looking at.
You absolutely do, because it is a master of disguise, and mostly because it looks so utterly ordinary.
Yeah, it's not exactly screaming danger, is it?
Not at all. It is the definition of unassuming. I mean, if you were to stumble across Cortinarius rubellus in the forest, it wouldn't trigger any evolutionary alarm bells.
Right, it doesn't look like the classic poisonous mushroom you see in fairy tales.
Exactly. It isn't bright red with those little white warning spots like the Amanita muscaria. It's literally just a medium-sized brownish mushroom blending into the leaf litter.
So let's paint a clearer picture of it for everyone. The cap is relatively small, right? Like 2.5 to 8 centimeters across.
Yep, that's right.
And it starts out conical when it's young, and then as it ages, it sort of flattens out into a convex shape. But it does have one very notable physical feature.
The umbo.
The umbo.
Yeah.
Yeah, it has this sharp central umbo. It looks like a distinct pointed bump, almost, well, nipple-like, honestly, right in the dead center of the cap.
That's a great description. And the color is this rusty date brown. It isn't slimy to the touch or anything.
Right. It has a dry, fibrous, almost scaly surface. And if you pull it close to your face, it actually gives off a very faint, slightly spicy, radish-like odor.
Right. The radish smell is a subtle but key identifier. And if you trace your eyes down to the stem, which grows about 5.5 to 11 centimeters tall, you'll see a series of distinct yellow zigzag bands wrapping around it.
Okay, those bands are super important, right? Because they come from a specific structure.
They do. They are the remnants of a biological structure called a cortina, which, by the way, is where the genus name Cortinarius actually comes from.
Right, and a cortina is essentially a protective veil, isn't it?
It is. It's a cobweb-like partial veil that shields the young, developing gills of the mushroom before the cap fully expands.
Oh, so as the mushroom grows, that veil just rips.
Exactly. As the mushroom matures and the cap opens up like an umbrella, those delicate, cobwebby fibers tear apart. And the pieces that remain stuck to the expanding stem, that's what creates those yellowish, zigzagging bands.
That makes so much sense. But, the real tragedy of the deadly webcap isn't its physical description in a vacuum. It's what it looks like to a hungry forager holding a basket.
Oh, completely.
Because people aren't wandering into the woods intentionally seeking out a highly toxic webcap. They're picking it because they think they found culinary gold.
And this misidentification happens across multiple continents. Foragers consistently mistake the deadly webcap for highly prized edible mushrooms.
Like salacips, right? Which most people probably know as porcini mushrooms.
Right, salas, or even more commonly for chanterelles. Specifically the golden chanterelle or the yellowfoot chanterelle.
Which are huge in the culinary world.
Massive. And there are also documented cases of individuals out looking for a psychedelic experience who mistake it for the hallucinogenic magic mushroom, Psilocybe semelanciata.
Wait, really? Because of the shape?
Yeah, because of a vague resemblance in the cap shape and the environment they grow in.
Man, what a disastrous mix-up. But if you actually know the biology, and if you are paying close attention to the anatomical structures, there are stark differences, right? You just have to know to look for them.
You do. The most glaring anatomical difference is in the gills. The deadly webcap has true adnate gills.
Adnate, meaning what exactly?
Adnate simply means that the gills are broadly and perpendicularly attached directly to the stem. And as the spores of the webcap mature, those adnate gills turn a very distinct, deep rust brown color.
Okay, but a chanterelle doesn't actually have true gills at all, does it?
Right. If you flip a chanterelle over, you see what are called false gills.
Which are really just blunt ridges or folds of tissue that run down the stem. They look almost like melted wax to me.
That's a perfect visual. But I can easily see how someone in a rush, picking in the dappled shadows of a pine canopy, tossing dozens of mushrooms into a mixed basket, could miss that detail.
Oh, totally. You get complacent, you make a fatal error. And that deceptive nature didn't just fool amateur foragers either.
Yeah.
It managed to completely baffle the global scientific community for nearly a century.
It really did. It created what basically amounts to a series of taxonomic criminal aliases.
The history of how this mushroom was cataloged is so wild. It was first officially described in the scientific record back in 1887 in England by a prominent British botanist and mycologist named Mordecai Cubitt Cook.
Right.
He observed it, took his notes, and named it Cortinarius rubellus. And, in a perfect world, that would just be the end of the story.
But 19th century mycology was far from perfect.
But to put it mildly.
The thing is, fungi possess an incredible amount of morphological diversity, meaning their physical appearance can alter drastically depending on the soil, the climate, and the specific trees they're growing near.
So they basically shapeshift based on their neighborhood.
Exactly. And because of this ecological plasticity and, the lack of modern communication tools, isolated scientists in different countries kept discovering this mushroom over and over again.
Assuming they had found an entirely new species each time.
Exactly.
Right, because in 1953, the renowned mycologists Robert Kuhner and Henri Romagisi were trekking through the Swiss Jura Mountains, and they found a deadly brown mushroom growing specifically under pine and spruce trees.
And they documented it and named it Cortinarius speciosissimus.
While meanwhile, another mycologist named Robert Henry was working in the French deciduous forests. He found what he believed was a totally different mushroom because it was associating with beech trees instead of conifers.
Right, so he named his discovery Cortinarius orellanoides.
And it didn't even stop in Europe. Around the same time, Alexander Smith and Daniel Stuntz were exploring Mount Rainier National Park in the Pacific Northwest of the U.S.
And they found a toxic webcap in the old-growth forests there and named it Cortinarius rainierensis.
So you literally have a situation where the exact same biological organism is operating under a different name in England, Switzerland, France, and the United States.
It's changing its behavior to blend in, thriving with beech trees in one country, but exclusively associating with pine trees in another.
It's acting like an international fugitive changing passports at every border.
That's exactly what it's doing.
But I want to go back to Cook's original 1887 discovery in England for a second, because there's a specific detail in the historical record from our sources that just fascinates me.
The spore drawings.
Yes. When Cook drew the microscopic spores of his Cortinarius rubellus, he illustrated them as being fig-shaped, or like somewhat triangular.
Right.
But if you put those spores under a modern microscope today, they are very clearly ellipsoidal, basically rounded ovals.
And the spore shape is a critical diagnostic feature in mycology. I mean, if you are comparing a triangular spore to an oval spore, you are by definition looking at two different species.
Right, so Cook simply drew it wrong. Maybe his equipment was faulty, or the dried specimen he was looking at had degraded over time. But the consequence of that one simple 19th century drawing error must have been massive.
Oh, what?
I mean, scientists in Switzerland looking at the round spores of their Speciosissimus would look at Cook's drawing of the triangular rubellus spores and logically conclude they were dealing with completely different organisms. How much did this simple drawing error delay the scientific community from realizing they were all dealing with the exact same deadly mushroom?
It created a decades-long bottleneck in toxicology. It significantly delayed the realization that multiple geographic regions were battling the exact same clinical poisonings.
That's wild.
It wasn't until the 1980s, through the painstaking deductive work of mycologists like Klaus Hyland and eventually the advent of modern DNA barcoding, that the scientific record was finally corrected.
Because DNA sequencing allowed us to look past the physical shape of the mushroom.
Right, past the physical shape, past the trees it associated with, and look directly at its genetic code.
And the genetics proved that the fugitive was just one species all along. Whether it was in a French beech forest or a Washington state pine forest, it was all the same highly toxic lineage.
Exactly, a lineage that engages in obligate ectomycorrhizal relationships.
Ectomycorrhizal meaning it forms a symbiotic, nutrient-sharing network with the root systems of whatever trees happen to be in its environment.
Exactly. And once the taxonomy was consolidated back to the original name, Cortinarius rubellus, toxicologists could finally focus all their attention on the single unifying feature of this species across the globe.
Which is the highly specialized, remarkably stable chemical compound it produces.
Yes.
So we've established how it hides. Now we need to look at the actual weapon it carries. Because this isn't a generic, broad-spectrum poison, is it?
Not at all. It's an incredibly precise chemical assassin called orellanine.
Let's unpack orellanine. What are we looking at chemically?
From a biochemical perspective, orellanine is fascinating. It belongs to a class of compounds known as bipyridines.
Okay.
Specifically, it is 3,3,4,4,4 tetrahydroxy 2-part-2 bipyridine N dioxide.
Wow, that is a mouthful.
It is. But structurally, it consists of two pyridine rings linked together, adorned with hydroxyl groups and nitrogen oxides.
But even without an organic chemistry degree, the moment you hear bipyridine, you should be concerned.
You really should, because the structure of orellanine is remarkably similar to synthetic bipyridyl herbicides.
Like paraquat and dequat.
Exactly, and those are notorious, highly restricted weed killers known for causing massive oxidative damage and cellular chaos in whatever tissue they touch.
The fact that a fungus, just growing quietly in a subalpine forest, naturally synthesizes a molecule so structurally akin to a modern synthetic industrial herbicide, that is a testament to the immense raw power of evolutionary biochemistry.
It's incredible, and the mushroom is absolutely packed with this compound.
The numbers in the toxicology reports are shocking. If you take the dried weight of the mushroom, you will find between 7,800 and 9,400 milligrams of orellanine per kilogram in the caps alone.
It's a massive concentration.
And in the stems, you're looking at 4,200 to 4,800 milligrams per kilogram. It's even heavily concentrated in the microscopic spores themselves. It is practically sweating the toxin.
It is.
But, and this is a big question, it doesn't carry the poison in an active destructive state while it's just sitting in the forest, does it?
No, it doesn't. If the active form of orellanine were freely floating around inside the mushroom's own tissues, it could be detrimental to the fungus itself.
That makes sense. It would poison itself.
Right. So instead, it utilizes a brilliant storage mechanism. Inside the mushroom, orellanine exists primarily as mono- and diglucosylated derivatives.
Glucosylated, meaning attached to glucose.
Exactly. The most prominent form is 4,4,diglucopyranoside. So in simple terms, the active-reactive parts of the toxin are chemically bound up with sugar molecules.
I picture this glucoside form like a locked smuggler's suitcase. Or, maybe even better, like those thick plastic safety caps you find on the terminals of a new car battery.
That's a really good analogy.
Right. You have this incredibly dangerous, highly reactive cargo. But as long as those sugar caps are firmly in place, the molecule is stable. It can't spark. It can travel harmlessly.
Precisely. But the mechanism designed to melt those safety caps away is where the biology gets truly diabolical.
Because it waits for the perfect environment.
It does. The chemical bonds holding those sugar molecules to the toxin are highly sensitive to an aqueous, acidic environment. They are perfectly stable in the damp soil of the forest.
Right.
But when a human ingests the mushroom, it travels down into the stomach, plunging the compound into a bath of concentrated hydrochloric acid.
So the stomach acid rapidly hydrolyzes the compound. It essentially melts those plastic safety caps right off the battery terminals.
Exactly. The acid breaks the sugar bonds, and suddenly the free, highly reactive, lethal orellanine toxin is released directly into the gastrointestinal tract.
And from there, it is rapidly absorbed into the human bloodstream.
Yes, and once it's in your system, there is no culinary trick to save you.
Right, because you can't outcook this chemical.
Not at all. The resilience of the orellanine molecule is a complete nightmare for food safety. It is extraordinarily heat stable.
So boiling the mushrooms in water.
Does nothing. Frying them in a skillet, freezing them for months, putting them in a food dehydrator, none of it does absolutely anything to degrade the molecular structure of the toxin.
Wow.
In fact, if you happen to cook the mushrooms in an acidic base, say like a vinegar or wine reduction stew, you might actually expedite the hydrolysis process.
Oh no. So you're releasing the free toxin into the broth before you even take a bite.
Exactly. You're basically doing the stomach's work in the pan.
Okay, let's unpack this from an evolutionary standpoint, because this brings up a really compelling question.
Sure.
Usually, when a plant or a fungus develops a defensive poison to protect itself from being eaten, it wants the predator to learn a lesson, right?
Typically, yes.
The poison tastes incredibly bitter, or it causes the animal to vomit violently within minutes. The animal gets sick, realizes the plant is bad news, and never eats it again. The species is protected.
Right, classical conditioning.
Exactly. But orellanine doesn't taste bad. And as we'll discuss in a moment, it doesn't do any damage until weeks after the mushroom has been completely digested. The animal dies, but it doesn't learn anything, and it doesn't warn its herd. So what is the evolutionary advantage of a toxin that doesn't show its hand until weeks after the mushroom has been digested?
That question perfectly highlights how humans tend to view nature purely through a mammalian lens.
Oh, interesting.
We assume everything in the forest is either trying to feed us or kill us. But the evolutionary target of orellanine was almost certainly not humans, deer, or any large foraging mammal.
Really? Then what is the chemical actually designed to fight?
Research into the specific properties of orellanine points toward the microscopic warfare happening in the soil. Orellanine actually has profound phototoxic properties.
Phototoxic, meaning it reacts aggressively to light.
Yes, and laboratory extracts have demonstrated that it acts as a severe inhibitor to the growth of soil bacteria, particularly strains like Bacillus subtilis.
Wait, so it's essentially a fungal antibiotic.
Basically, yes.
It's a weapon designed to clear out bacterial competitors in the damp, crowded real estate of the forest floor, ensuring the mushroom's mycelium has exclusive access to the nutrients in the soil.
It's an antimicrobial agent and potentially a defense against microscopic nematodes as well.
So the fact that this soil-level antibacterial compound happens to have the exact molecular shape required to utterly annihilate the kidneys of a large mammal weeks after ingestion
Is incredibly just a tragic, accidental byproduct of its actual ecological function.
an accidental biological smart bomb. That is a chilling thought,
Very much so.
which perfectly leads us into the timeline of the poisoning itself. Because once that stomach acid melts the sugar caps and the orellanine enters the bloodstream, the real horror begins.
The clinical progression is unlike almost anything else.
Right, because unlike cyanide or arsenic or even the amatoxins found in the death cap mushroom, orellanine takes its time. It leads to a uniquely devastating clinical timeline known as the Orellanine syndrome.
And the defining characteristic of the Orellanine syndrome is its unprecedented latency period. It completely separates the cause from the effect in the patient's mind.
Let's map out the physiological journey of someone who eats that stew we talked about in the intro.
Okay.
About 2 to 3 days after the meal, the patient enters what toxicologists call the prerenal phase.
Right.
And the symptoms here are incredibly mild. You might feel a bit fatigued, experience some slight nausea, maybe a minor headache, or you might vomit once or twice.
It is the clinical presentation of a very minor, nonspecific viral infection. 99% of people would attribute it to a mild stomach bug or maybe something they ate at a fast food restaurant the day before.
And then those symptoms just vanish. You feel totally fine. You go back to normal life.
But inside your bloodstream, the orellanine is circulating.
And this latency period, the time before the actual devastating renal phase begins, can last anywhere from 2 to 21 days,
Yes.
with a median time of about 8.5 days before the severe symptoms hit.
And during those 8.5 days of perfect silence, the free orellanine is methodically moving through the body. It filters through the liver, the heart, the brain.
But it leaves those organs completely untouched.
Completely.
Which is crazy. Why does it ignore the heart and the liver? How does the toxin know to only attack the kidneys?
This is where the hyper-specific targeting of the molecule really comes into play. The human kidney is made up of millions of tiny filtering units called nephrons.
Right.
And within those nephrons are the proximal tubular cells. The job of these specific cells is to reabsorb water, glucose, and essential nutrients back into your bloodstream after the kidney has filtered the raw fluid.
Okay, got it.
To do this, the proximal tubular cells are aligned with specialized transport proteins called organic cation transporters, or OCTs.
Organic cation transporters. So these OCTs act like selective bouncers at the door of the cell, pulling in the good molecules and keeping out the bad ones.
Precisely. But orellanine essentially has a fake ID. Its molecular shape perfectly mimics the organic cations that the OCTs are naturally looking for. So the kidney cells actively grab the orellanine out of the blood and pull it deep inside themselves.
Actively concentrating the toxin within the proximal tubular tissue.
Yes. And because the liver and the heart don't have these specific transporters, the toxin simply floats right past them.
It is a literal Trojan horse mechanism at the microscopic level. The cell invites its own assassin inside.
It really does. And once the orellanine is inside the proximal tubular cell, it initiates a brutal four-pronged cellular attack.
Okay, let's break down this attack. What's the first prong?
The first prong is an immediate blockade on protein synthesis. The toxin binds to the cell's internal machinery and simply halts the production of new proteins.
Man. So if the cell can't synthesize proteins, it can't perform basic maintenance, can't repair a damaged membrane, or build the enzymes it needs to survive. It's essentially taking out the cell's repair crew right at the start.
Exactly. You lock out the repair crew.
What is the second phase of the sabotage?
Prong 2 is where that structural similarity to the paraquat herbicide shows up.
The weed killer comparison.
Right. The orellanine engages in a process called redox cycling. It enters into an endless, rapid-fire loop of stealing and passing electrons within the cell.
And that creates a problem.
A massive problem. This constant electron theft generates massive amounts of reactive oxygen species, or ROS.
These are highly unstable, volatile molecules, right?
Extremely volatile. These reactive oxygen species violently interact with the lipids that make up the cell's outer membrane in a process called lipid peroxidation. The ROS are quite literally shredding the walls of the cell from the inside out.
So we have a saboteur who has locked out the repair crew,
Right.
and now they're pressing the accelerator straight to the floor, creating all this explosive oxidative stress and tearing the cell apart.
Exactly.
But wait, normal healthy cells have defenses against oxidative stress, don't they?
They do. Healthy cells are packed with natural antioxidant defenses specifically designed to neutralize reactive oxygen species, molecules like glutathione, NADPH, and ascorbate.
And just to clarify for everyone listening, ascorbate is simply vitamin C, right?
Yes,
That acts as the cellular fire extinguisher to put out the ROS fires.
Yes, but prong 3 of orellanine's attack specifically targets and severely depletes the cell's reserves of ascorbate, glutathione, and NADPH.
Oh, man. So keeping with the analogy, the saboteur isn't just pressing the gas pedal to the floor to create the oxidative damage. They have simultaneously cut the brake lines and emptied the fire extinguishers.
Yes. The cell has absolutely no way to slow the damage down.
It guarantees total structural failure.
It does. And just to ensure the job is absolute, we have prong 4. Orellanine aggressively inhibits vital cellular enzymes, most notably alkaline phosphatase.
How does inhibiting alkaline phosphatase kill the cell?
Well, alkaline phosphatase is crucial for the transport of metabolites across cell membranes, and it plays a key role in the function of the mitochondria, the energy-producing power plants of the cell.
Right.
By inhibiting this enzyme, the toxin effectively chokes off the mitochondria, starving the cell of its energy supply.
So the power plant is shut down, the repair crew is locked out, the fire extinguishers are empty, and the walls are being shredded by oxidative explosions.
Total irreversible devastation of the proximal tubular cells.
And because of that long, silent latency period, by the time the patient finally feels the symptoms of this microscopic war, the damage is already catastrophic.
Sadly, yes. When the patient enters the final phase of the Orellanine syndrome, their kidneys are actively failing.
What does that look like clinically?
The clinical presentation starts with intense, unquenchable thirst, a condition called polydipsia. They also experience a severe burning sensation in their mouth and lips.
Wow.
And eventually they develop oliguria, which progresses into arnuria, which is the complete and total inability to urinate.
Because the proximal tubular cells have been entirely destroyed, so the kidneys have simply stopped processing fluid altogether.
Exactly. And this is usually the moment a patient rushes to the emergency room.
But think about the diagnostic nightmare for the physician here. A patient presents with acute, unexplained renal failure. How many patients are going to remember to tell their doctor about a random mushroom stew they ate 2 or 3 weeks ago?
Almost none, unless the patient happens to be an avid forager and specifically brings it up, or the physician is highly trained in regional toxicology and thinks to ask about wild mushrooms. The diagnosis is frequently severely delayed.
Because the doctors are looking for other things.
Right, they are looking for infections, autoimmune diseases, heavy metal poisoning, while the true culprit is a fungal meal from weeks prior.
There is a very famous, incredibly tragic case that perfectly illustrates this diagnostic gap and really the sheer potency of the toxin.
The Nicholas Evans case.
Yes. In 2008, the author Nicholas Evans, who was famous for writing the novel The Horse Whisperer, was on holiday in the Scottish Highlands. He was with his wife, his brother-in-law, and his sister-in-law. They went out for a walk in the woods and gathered what Evans firmly believed were Sepp's edible porcini mushrooms. But he had accidentally picked a cluster of Cortinarius rubellus.
Which, as we know, is an easy mistake to make.
Exactly. So they took them back to the estate, cooked them in butter and parsley, enjoyed a lovely dinner, and just went about the rest of their vacation.
And it wasn't until weeks later, long after they had returned to their normal lives, that the entire family started experiencing catastrophic, cascading kidney failure.
Evans and several members of his family ultimately required kidney transplants to survive.
It's devastating.
And the terrifying part of that story is how little of the mushroom they actually consumed. We aren't talking about eating platefuls of the fungus here.
No, the lethal dose of Orellanine is shockingly low. Clinical toxicology data indicates the lethal threshold is just 0.04 milligrams of toxin per kilogram of body weight.
0.04 milligrams, that is almost nothing.
In practical, real-world terms, a healthy adult eating just 2 or 3 small webcap mushrooms is ingesting enough Orellanine to permanently destroy their renal function and mandate lifelong hemodialysis.
And once that inuria sets in, once the patient stops producing urine, the doctors can't just put them on a dialysis machine to filter the poison out of their blood, can they?
No, because by the time the symptoms peak, the toxin is no longer in the blood.
Wait, really?
Yes, Orellanine has such a high affinity for the proximal tubular cells that it rapidly leaves the circulatory system and binds incredibly tightly to the kidney tissue itself.
Wow.
You cannot dialyze the poison out of the blood because it has already entrenched itself in the organ.
That's terrifying.
It gets worse. It binds so securely that clinical pathologists analyzing kidney biopsies using high-performance liquid chromatography or HPLC mass spectrometry can still detect high concentrations of Orellanine in the necrotic kidney tissue up to 6 months after the patient ate the mushroom.
6 months later.
6 months later.
The poison just sets up a permanent camp in the ruins of the organ.
Yeah.
It completely destroyed. It is a bleak, terrifying biological mechanism.
It truly is.
But, and this is the huge pivot in our deep dive today, this
yeah.
exact mechanism, this highly specific, completely unstoppable organ-targeted cell death, is the very thing that caught the attention of oncologists.
Yes.
Because for a toxicologist, a molecule that permanently destroys an organ is a nightmare. But for a cancer researcher staring down a tumor that refuses to die, that exact same mechanism looks like an unprecedented weapon.
It represents a remarkable philosophical and medical pivot. We have thoroughly established that Orellanine is a flawless, uncompromising assassin of proximal tubular cells, right?
Right. Flawless.
So the logical next step in the scientific process is to ask, what if we could take that flawless assassin, point it away from a healthy person, and aim it directly at an enemy we desperately need to destroy?
And the enemy in this scenario is clear cell renal cell carcinoma, commonly abbreviated as CCRCC.
Correct. CCRCC, along with papillary renal carcinoma, represent the most common and by far the most aggressive forms of kidney cancer in humans.
Okay.
And the critical biological link here, the entire foundation of this deep dive, is that the vast majority of these cancers originate from the exact same proximal tubular cells that Orellanine naturally evolved to target.
This is the massive aha moment in the research. The cancer cells aren't some alien invader. They're just heavily mutated, violently dividing versions of the cells the mushroom toxin already knows exactly how to kill.
Exactly. And finding a way to kill CCRCC is one of the holy grails of modern oncology.
Why is that? Are they particularly hard to treat?
Very. These specific cancers are incredibly dangerous because they are highly vascularized and have a high frequency of metastasis.
Meaning they spread easily.
Right. They shed cells into the bloodstream that take root and spread to the lungs, the bones, the liver, and the brain. Furthermore, they are notoriously resistant to conventional therapies.
Like chemo.
Standard systemic chemotherapy and standard radiation treatments frequently fail to make a dent in metastatic CCRCC. Once the cancer has spread beyond the primary kidney, achieving a cure has historically been incredibly difficult.
But here's the biological loophole that the researchers found. When those cancer cells break off from the kidney and metastasize into the lung or the bone, they don't lose their original identity, do they?
No, they don't. They still carry the biological signature of a proximal tubular cell.
Even in the lung.
Even in the lung. Despite being mutated, metastatic CCRCC cells retain the specific surface receptors and the transport mechanisms of the kidney cells they originated from. Most importantly, they still possess those organic cation transporters, the OCTs we discussed earlier.
The bouncers with the fake idealist are still working the door, even if the door is now located in a lung tumor.
Precisely. Which means, theoretically, if you introduce Orellanine into the bloodstream of a cancer patient, the toxin will circulate through the body, ignore the healthy lung tissue, ignore the healthy bone tissue.
But the moment it bumps into a metastatic CCRCC tumor,
it will recognize that proximal tubular cell signature. The tumor's OCTs will actively pull the toxin inside, and Orellanine will execute its unstoppable four-pronged attack.
halting protein synthesis, generating ROS, depleting ascorbate, and shutting down the mitochondria.
Killing the cancer from the inside out.
This theory brings us to a major, tangible breakthrough in the pharmaceutical world. A Swedish biotechnology firm called Oncorina recognized this potential and developed a proprietary drug called ONC-175.
Right, ONC-175.
And it is a synthetically produced, highly purified version of the Orellanine toxin. And they didn't just write a paper theorizing about it, they actually tested it in the lab.
The preclinical trials for ONC-175 are some of the most compelling readings in modern oncological literature.
How did they test it?
The researchers used nude rats.
Nude rats.
Yeah, they are specially bred, immunocompromised laboratory rats used extensively in cancer research, so their bodies don't reject foreign tissue. They implanted these rats with human CCRCC xenografts.
So to put it simply, they surgically gave the rats human metastatic kidney cancer.
Exactly. And then they administered the synthetic Orellanine toxin.
What did the data show?
The results were nothing short of triumphant. Following brief, carefully calibrated treatments with this synthetic toxin, the researchers observed the eradication of over 90% of the viable tumor mass.
90%?
Yes. The human cancer tumors inside the rats literally necrotized, collapsed, and shrank dramatically.
That is unbelievable.
And the most vital data point of the entire study was the safety profile concerning the other organs. Because of Orellanine's profound, evolutionarily ingrained organ specificity, the toxin entirely ignored the rat's healthy heart tissue, liver tissue, and central nervous system.
It operated like a guided missile, going solely after the kidney tissue and the kidney cancer cells.
Exactly.
Okay, but if we extrapolate that data to a human patient, there is an incredibly obvious medical hurdle we have to address.
Right.
The drug destroys proximal tubular cells. Mm-hmm. It doesn't differentiate between a cancerous proximal tubular cell in the lung and a healthy proximal tubular cell in the patient's actual kidney.
It doesn't.
So if you give this drug to a patient to cure their metastatic cancer, wouldn't the drug just completely destroy their healthy kidneys in the process? I mean, you'd be saving their life from the cancer, but condemning them to end-stage renal failure and lifelong dialysis?
That is the exact ethical and physiological paradox of this treatment. You cannot ethically administer this drug to a patient who still possesses healthy, functioning kidneys because you would be intentionally inducing the horrific Orellanine syndrome we detailed earlier.
Right. You'd be poisoning them.
But the researchers at Oncorina and the medical review boards found a darkly brilliant solution to bypass this hurdle. It is the foundation of the Phase 3 clinical trial currently greenlit by the FDA, known as the Oncorella-1 trial.
How do you bypass the fact that the drug destroys kidneys?
You bypass it entirely through highly specific patient selection criteria. The Oncorella-1 trial does not enroll early-stage kidney cancer patients.
Okay.
It only enrolls patients who have advanced metastatic kidney cancer, who have completely exhausted all other conventional treatment options, like immunotherapy or kinase inhibitors. And this is the critical linchpin, who are already on chronic hemodialysis due to end-stage renal disease.
Oh, wow. The elegance of that is staggering. Their kidneys have already failed, either from the sheer burden of the cancer itself or as collateral damage from years of previous highly toxic treatment.
Exactly. These specific patients have zero remaining kidney function left to protect. The organ is completely lost, and they are already fully reliant on a dialysis machine to filter their blood.
So there's nothing left to lose, kidney-wise.
Exactly. Because the healthy kidney tissue is already gone, physicians can safely administer high intravenous doses of ONC-175.
So the synthetic Orellanine enters the bloodstream, searches for healthy kidney cells to destroy, finds absolutely nothing.
And is therefore forced to hunt down and exclusively annihilate the metastatic kidney cancer cells hiding in the lungs, the bones, or the lymph nodes.
If you step back and look at what this actually means, it is profound. You're taking patients who are at the absolute end of the medical road, who are relying on machines to stay alive, and we are utilizing a lethal forest poison, a toxin with no known antidote, a chemical that has tragically killed or maimed people who accidentally foraged it for a family dinner, and we are deploying it as a highly targeted, life-saving smart bomb directly into their tumors.
It represents the ultimate repurposing of nature's inherent weaponry. We are taking the exact biochemical mechanism that makes the mushroom so lethal to a healthy human, and we're using it as a specialized microscopic scalpel to save a human life that conventional medicine had completely given up on.
It perfectly illustrates that the line between a deadly poison and a miracle medicine is entirely defined by context, dosage, and the specific target.
100%.
Thinking back to the Nicholas Evans story, the tragedy of losing your natural kidneys to a simple mistake in the woods is unimaginable. But the idea that understanding that exact same chemical tragedy could result in the first truly curative treatment for advanced drug-resistant renal cancer, it completely reshapes how you view toxicity.
It forces a total reevaluation of the natural world. Toxicity is, at its core, just potent biological activity. Orellanine isn't inherently evil or malicious. It is simply a highly complex molecule executing the exact chemical reaction it evolved to perform over millions of years.
It's doing its job.
Exactly. When that molecule interacts with a healthy hiker, it results in a devastating medical tragedy. But when that exact same molecule is aimed at a metastatic ccRCC tumor, it becomes a medical miracle.
We have covered an incredible amount of biological and historical ground today, so let's do a quick recap to tie all these threads together for everyone listening.
Sounds good.
We started our journey in the damp leaf litter of the forest with Cortinarius rubellus, the deadly webcap, a frustratingly unassuming brown mushroom with an umbrella cap and adnate gills that seamlessly mimics prized culinary mushrooms like chanterelles and porcinus.
And which managed to spend a century confusing the greatest mycologists in the world by operating under multiple aliases across Europe and North America.
Yes. We then examined its hidden payload, the bipyridine toxin Orellanine. We looked at how it safely travels in a locked glucoside suitcase, only to have those sugar safety caps violently melted away by human stomach acid.
Releasing a chemical that resists all forms of heat and cooking.
We tracked the agonizing slow-motion horror of the Orellanine syndrome. The 2 to 3 weeks of complete silence before the toxin, having been actively pulled into the kidneys by the OCT transporters, completely obliterates the proximal tubular cells.
By shutting down protein repair, emptying the cellular fire extinguishers, and flooring the oxidative accelerator to shred the cell to pieces.
And finally, we looked at how oncology flipped the script. We examined ONC-175 and the groundbreaking Oncorella-1 trials, where this exact unstoppable mechanism of cell death is being tested in dialysis patients, acting as a guided missile to eradicate metastatic kidney cancer cells that conventional medicine cannot touch.
It is a journey that bridges the muddy boots of a 19th century botanist to the sterile IV bags of a 21st century cancer ward.
It really is. But before we sign off, I want to leave you with a broader perspective to think about the next time you look at the natural world.
If we look at the big picture of what the Oncorella-1 trial represents, It proves that nature is, without a doubt, the greatest, most prolific biochemist on Earth.
Absolutely.
It has had hundreds of millions of years of unrestricted research and development to create molecules with specificities and mechanisms that human pharmacologists can barely dream of synthesizing from scratch.
So true.
If the Deadly Webcap's lethal, organ-destroying payload can be so elegantly repurposed into a precision oncological tool, it raises a truly provocative question.
And what is that question?
How many other supposedly incurable human diseases might eventually be solved by carefully examining the toxic, overlooked, and dangerous weeds, venoms, and fungi growing right now in our own backyards?
Yeah.
Humanity spends so much time and money trying to eradicate poisonous things, trying to pave over the dangerous aspects of nature, but the chemical cure for the next great medical hurdle might currently be hiding in the venom of an aggressive wasp, the sap of a noxious invasive weed, or the gills of a toxic brown mushroom.
That is a phenomenal, humbling thought to leave on. Thank you so much for joining us on this deep dive. We hope you walk away from this feeling a renewed sense of awe and insane curiosity about the unseen biological warfare happening in the woods around you. But keeping in mind that beautiful autumn hike we talked about at the very beginning, maybe be just a little bit more cautious and check your spore prints the next time you decide to forage for your dinner stew. Stay safe, stay curious, and we'll catch you on the next deep dive.